Well, welcome everyone to the M-Cubed seminar series. Today I'm pleased to present an oldie but goodie. Rich Rotunno, oldie and goodie for many reasons, perhaps, but Rich is a senior scientist here at Mesoscale Meteorology Laboratory. He got his PhD from Princeton in geophysical fluid dynamics in 1976. That was back to the Civil War, wasn't it? Right after the... Richard has a fairly wide range of interests, nothing too great. He's done studies in dynamic meteorology, including tornadoes, rotating thunderstorms, squall lines, hurricanes, polar lows, mid-latitude cyclones, fronts, mountain valley and sea breeze circulations, coastally trapped disturbances, dynamics of density currents, vortex stability, and atmospheric predictability. Really? Are you running for Congress or something? Has this been checked over? Despite this rather narrow range of interests and contributions, he has managed to win a few awards. He's won the Banner I. Miller Award in the tropical community twice, once with Kerry Emanuel, once with George Bryan. He's won the Chani Award from the AMS, managed also to win the Rossby Award from the AMS, and most important, he received a Lifetime Achievement Award from the Severe Local Storms Committee. Isn't that given to people who don't get the Oscar during their careers or something, and that's all that they get is a Lifetime Achievement? Anyway, yeah. Well, one thing we do know about Rich is he's always very unpredictable, and today's seminar might teach us something about why he's so unpredictable. So.
All right, good afternoon, everyone. Thanks for coming. Today's title of today's seminar is based on a paper of the same title that has just appeared in JAS. It's in the January 2023 issue of Journal of Atmospheric Sciences. So the agenda for the talk, I have a lot of background. The background will be a little bit more than it'll be almost 60% of the talk. But the first background one is sort of the basic science and some of the evidence in favor of the basic science. Background two will be some of the evidence against the basic science that was based on very simplified models. And results are basically the conflict resolution. So it'll be a conflict resolution, I hope, of the background one and background two. And then a little bit at the end with restating the conclusions and a bit of an epilogue. So in many ways, the history of this subject, predictability, is intertwined with the history of science at NCAR. Back in 1960, Phil Thompson was brought in by Walter Roberts to, I think, hire, it says on the UCAR website here, to hire the sort of the best and the brightest of scientific minds to populate the ranks of NCAR science, which we are all sort of the heirs of today. But anyway, one of the things Phil Thompson recognized was early on recognizing that the atmosphere is turbulent all the way through the large scales. And so he, since it was known you couldn't predict in detail turbulent flows, there was some doubts raised about what you could do with the atmosphere. And so he was one of the first to express this in the paper in 1957, where he states that the predictability of the atmosphere is not merely the extent to which its behavior is predicted in practice, but the extent to which it is possible to predict it with a theoretically complete knowledge of the laws that govern it. Ed Lorenz, who was also a frequent visitor in the early days of NCAR, in fact until his death, he was every summer here at NCAR. He had an answer to this question, about to Phil Thompson's question. And this was in a paper, a seminal paper of 1969, Tellus. And he came up with a rather startling proposal. And that proposal is this. He said, based on a model of turbulence, he said, for any future time, there's a limit below which the error cannot be reduced, no matter how small the initial error, if not zero, is made. And there's a very nice essay by Tim Palmer and colleagues, where he notes that this is a radical proposition. And it was if you're thinking about just mere sensitivity to dependence on initial conditions, this is something else. The idea of a flow with many scales of motion being not predictable. So this famous figure is from Ed Lorenz's paper, and I'll spend a little bit of time on explaining it because you're going to see a lot of figures kind of like this in this talk. So what was his model? Model was a model of theoretical of a homogeneous isotropic turbulence in a statistically steady state. The energy spectrum is sort of the given of the model, say it's the background model. And back in the late 50s and the 60s, they started formulating the predictability problem as being one where you have the energy spectrum, of course, is based on an ensemble of flows being averaged. And so you could think of sub ensembles, which are the same in every way except that they're decorrelated at say a certain scale. So if I point over here to this, you can see that there's the background energy spectrum given in the darker curve, whereas the thinner lines represent what they call the error energy spectrum, or officially the decorrelated energy spectrum. So for scales that are smaller than, say, the given by this line here, the two subensembles have the same energy, but they're completely decorrelated, and so the forecast is basically no better than the climatology, which is given by the background. Okay, and so what Ed's model did was then calculating the time it takes for error to grow from one scale to the next, and say, suppose like your target is 5 days, and if you didn't already notice, the scales, long scales are on the left and small scales are on the right. So this particular calculation he did is started from some impossibly small scale, a few meters of error. And then you can see that in 15 minutes, it rapidly grows to this much. And the way this diagram is constructed is that each one of these lines represents a doubling of the error. So basically the area under this curve doubles every time you see a line being drawn here. And so when the thin line hits the background line, then the forecast is no better than a random draw from a statistical distribution of states that make up the error spectrum. So back then, when they were thinking about numerical weather prediction, they were running a barotropic model. They had a network of radiosondes, and the question was, well, how much more benefit can we get by increasing the number of radiosondes? Can we, suppose we could have 4 times as many radiosondes. So in terms of Ed Lorenz's diagram here, we'd say, well, okay, suppose you have a network that's 156 kilometer, because you can see that on its resolving power. And suppose you go through the time and expense to reduce it to a network that has, what does that say, 39 kilometer resolution. So you'd start out with an error here instead of an error here. Now, if the target is 5 days, this increase of 4 times would basically decrease the initial error by half. But the expectation here is well, you're not going to decrease your target time error by half. You're just going to decrease it by these 4 hours. So that was a rather pessimistic prediction. Saying, well, look, you could add more and more information at small scales, But those small-scale errors will just grow faster and faster. And so, it becomes a real live problem of cost-benefit analysis. Now, the caveat here is that all of these calculations were based on a minus 5/3 spectrum that was assumed to extend from mesoscales, microscales, mesoscales, and synoptic scales, all the way up to the peak here. And at the time of the writing of this paper, it was not yet known what the spectrum was at these larger scales. So, but the importance of the input spectra was noted in Ed Lorenz's paper. Now, Doug Lilly, who was the head of the group that preceded MMM, was part of this mix. It was a very intellectually stimulating time here at NCAR. And he came up with a simple scaling to understand how predictability works, and why it's so dependent on the background spectrum. So the proposal there is that you can formulate an error growth scale as a function of wave number. And the simplest thing to do is to take it as 1 over the advective scale at that wave number. The velocity scale, he proposed you could combine the wave number and energy spectrum. Don't forget, energy is the energy spectrum is energy per unit wave number. And so k times the E of k, all to the 1/2, would be a velocity scale. If you put that in here and join this k up with it, you get k cubed E of k. Now substitute in the power law, and you find that the error growth time scale as a function of wave number is k to this power, n minus 3 over 2. So if, for example, n is equal to less than 3, is equal to 5/3, for example, for 3D turbulence, then you would have limited predictability, because larger and larger k, smaller and smaller scales, means a very rapid time of error doubling. So every time you add more resolution, you get a larger k in the system. Larger k means that your error grows that much faster. Whereas at n equals 3, then all the growth rate, all the time scales are the same. So if the atmosphere was a minus 3 all the way down to small scales, we would have unlimited predictability, because every time you add resolution, you're adding the same amount of error growth time scale. So as Ed was writing this paper, Axel Wynne Nielsen was also a visitor to NCAR in those days, was finding that the atmosphere does obey a minus 3 spectrum, at least at large scales. And this was since verified by the famous Nystrom and Gage paper, based on commercial aircraft flying around the country and measuring spectra. And so this is from a paper by Bill Skamrock, where he summarizes this. This is the synoptic scales here, showing it follows a minus 3 law. And then down the PBL and the mesoscales, there's a minus 5/3 seems to be the fit. So the theoretical community came back to Ed Lorenz's model. It was kind of, as all first attempts are, they're kind of primitive. And it was a barotropic vorticity equation in which he assumed a minus 5/3 energy spectrum for the background. Now, it was not yet known at that time that the background, well, the barotropic vorticity equation is basically a 2D vorticity equation, and the consistent shape of the energy spectrum downscale from a large-scale forcing is k to the minus 3. And so Bob Kriegman, also a frequent visitor to NCAR in these early days, came up with the well-known result now that this shape should be k to the minus 3. So Leith and Kriegman, this is also coming out of NCAR back in 1972, came up with the first statistical models to predict not only the background spectrum, but also the shape of the error spectrum the shape and the time behavior of error spectrum. And so this one is doing basically these statistical predictability models are basically Navier-Stokes equations. You formulate an equation for the energy, and then you model the triple moments that come out of such an equation. It's very complicated, and it's not something we can go into here. But these statistical models gave a reliable, it passed a certain number of tests, and later on in terms of being compared to direct numerical simulations. So in this case here, the three-dimensional turbulence model with a -5/3 spectrum, initializing with an error at small scales, it basically confirmed the Lorenz prediction, showing that the small scales grow rapidly in both in amplitude and in scale. They go to larger scale over time. Whereas the 2D turbulence case, you start out with an initial amplitude here, initial error here, and it will kind of gradually shift over, and then assume kind of a self-similar shape after that. And you can tell from the, these are equal time increments on the spectra. And so here you can see that after this initial adjustment period, each of these have the same distance between the lines. So that means if one had started out with an even smaller scale initialization, it would just add another, it would add a commensurate amount of error at every step. Whereas here, if you start out at even smaller scales, it would grow even faster. So you can't win that race ultimately. Okay, to give you a little bit of flavor of what we mean by 2D and 3D turbulence, here's an example, courtesy Ned Patton, of 3D turbulent flow. And I'd like you to focus on sort of the big, your eye can focus on the big eddies kind of lumbering along, and then the smaller eddies here that develop and quickly kind of evolve and become bigger and bigger. Whereas 2D turbulence looks more like this. This is courtesy Bill Skamrak, Joe Klemp from the MPAS model. This showing 500 millibar vorticity evolving in time. And I don't know if you've ever been to Estes Park and watched the saltwater taffy machine going like this. And this is more like the saltwater taffy being bent round and round and round. All the scales have the same time scale. That's the property of 2D turbulence. So there are long strips of vorticity and curls of vorticity, but they're all moving at the same speed. The culmination of these ideas came in an award-winning paper by our colleague Falcojev, and in which he had two parallel simulations of a real climate, of a real period. In November, was it, of October 2012, including Hurricane Sandy, and had everything in it. And so he did the identical twin experiments, and starting from a small initial difference. And so what you get to see here is the difference kinetic energy. This would be like the E delta in the theoretical papers, and and the time counter is in the upper right over here, and I'll just let it play. So what you see is that what you'd expect is that the places where there are fast time scales, where there's convection over here over the Amazon and over the ITCZ along frontal zones, is where you see the errors, errors meaning the difference between these two forecasts growing most rapidly. And over time, what you'll see, this is the counter, we're at 5 days now. Over time, the whole globe is going to become red, meaning that the forecasts are as different as they can be within the confines of the climatology. And we're out to 10 days, and I'll quit after that. But you get the point. That starting from very tiny, imperceptible differences in temperature, the whole forecast changes after about 3 weeks. Falco did a spherical harmonic analysis of the error spectrum, showing that at early times the spectrum kind of grows up from small scales and heads towards larger scales, grows rapidly at first and slows down. And that's kind of reminiscent to what you see in the minus 5/3 analysis of the statistical predictability theory, whereas at large scales, it goes from it's more consistent with the findings from 2D predictability theory, where the spectrum reaches a self-similar shape and then grows up with the peak being determined by the peak of the forcing. In Falco's paper, he brought for comparison this paper by Chris Snyder and myself. What we did back in 2008 was that we took the Lorenz model, and we said, okay, well, if it's a 2D model, why don't we run it for for a consistent background spectrum, which is a -3 spectrum. And when you do that, you get a result which is very similar to the result I showed from the more sophisticated statistical models of Mattei and Lesueur. We also did the following here. We said, well, it's with a slight change of a few items in the equation, you can make this applicable to the surface quasi-geostrophic equations, which is basically, instead of advecting vorticity, you advect surface potential temperature. And details of which are not particularly important here, except the one detail is that it does have a consistent minus 5/3 energy spectrum for forced statistically steady flow. And when you do the error analysis, it looks just like what Ed Lorenz had done, where you get very rapid growth with small scales growing into large scales. So at this point, I thought everything was well in Wellville. We have a theory, it seems to kind of work. However, I'm moving to background 2. All was not well in Wellville. We had a paper here. I'm glad that the participants actually are here today, in which they found the following. Now I'm gonna flip their figure around, because everything that you have seen and will see have large scales on the left and small scales on the right. So this is the figure I just described to you. That was in Rotunno and Snyder, 2008. And here was this is a paper based on the NICAM model, which is over here now. And the NICAM model is a Japanese model. They ran a aquaplanet, and what I'm showing here is they did longitudinal spectra of both the background and the error, and averaged from 5 north to 5 south. And I'll let them describe it here. The error spectrum, meaning these lines here, fill up the saturation spectrum vertically, up amplitude, rather than horizontally upscale. So meaning instead of going this way, the error goes this way. Large scales grow just as rapidly as small scales, and they do so before the small scales saturate. So these lines shoot across the page like this instead of going one by one. So this is basically the upscale versus up amplitude. So I didn't know quite what to make of it at the time. I thought, as getting to be my age, I said, you wake up with a pain and maybe it'll go away. And so, but it came back. And so it came back, his paper by Dale Duran, and he was looking at, with his colleagues, cases in the Pacific Northwest winter limited area model, Ensemble, and the Ensemble average error. So he had an Ensemble that started with different initial conditions, and you get the initial error then with this spectrum showed given in the black line, and over time it progressed as follows, and I'll just quote them here. No evidence of small-scale perturbations developing rapidly and transferring their influence upscale. Instead, the large-scale perturbations appear to grow more rapidly during the first 12 hours than those at the smallest resolved scales. So I said, well, I don't know. It's Pacific Northwest, probably not much convection, limited area model, who knows what's going on. But then up the ante here, Dale did a idealized mesoscale convective system model. They had a -5/3 spectrum, periodic boundary conditions all around. And they had an ensemble of runs, and this is the initial difference among the ensembles was given by this blue line here. And then in time, you could see that it, well, let them say what they saw. Both small and large scale errors grow primarily up in amplitude at all scales rather than through an upscale cascade between adjacent scales. And the dashed lines here are simply repeating these experiments but artificially reducing the initial error. And they do the same thing. And 2020, Falco asked me to do an internal review of his paper. And what Falco was after in this paper was to see if we can localize the predictability characteristics of different latitude belts. So here was the tropics, and here was the mid-latitudes, and here's the polar cap. And what he did is he did longitudinal spectra and averaged over the latitudinal belt. And he produced spectra like this, which all exhibited this flat line behavior at the large scales. And I asked him at the time, I said, Falco, what about this? How come, and we didn't know what to make of it at the time. But Falco, as he was interested in, the times to saturation here, he wasn't particularly concerned about what was going on at very large scales. But this was certainly in the back of my mind. Until the summer of 2021, Dale sent me an advanced copy of this paper. And some of you might remember Dan Uvaris, who was here recently. And he showed this. Now this is for a case of baroclinic wave with moist convection. And the thing that sort of jolted me was this statement here that, and the statement here, I'm going to come back to this, the content of the statement, but I just want to point out, he said that both computational methods, and those words, both computational methods, came up to, wait a minute, now you're saying that using the very same data, you can make this flat line appear, or make it not appear? The one here on the left, the 2D, that's much more congenial to statistical predictability theory, whereas the one on the left here is what has been cited in all the papers and background too. So I was wandering the hall ruminating about this, and I bumped into Chris Snyder and around this time, and I said, well, and I started telling him about this paper, and he started telling me about a paper he's been reviewing with a similar kind of finding with the flat line spectra, predictability in the predictability world. And we started brainstorming a bit, and I'm going to tell you what we came up with, and then I'll tell you how we brought Falco into the mix. So here's what we did. We took a hypothetical error field, and here's the hypothetical error field given by this picture here. It's homogeneous, isotropic, but it has a dominant error scale. And it's kind of step zero in all these in statistical predictability theory is that the k that the wave number that's being used is the magnitude of the wave number vector, k squared plus L squared. And so it's not interchangeable with just the one-dimensional k. So the two-dimensional spectra of this field is basically a donut. And the donut, and the way to get a scale from that is you pick out a geometrical k squared plus L squared, kappa, in this we're calling it, and you integrate around the circle, and you produce a plot given by the black line. And this is, this is like the things you see in statistical predictability theory that have a peak at a certain scale. Now, we thought, well, what if we just take the same field and analyze it the way that folks are analyzing their data in the models I've cited, in which you take longitudinal spectra and at every latitude and then average. And the result is the blue line. And you can see it has that kind of flat line structure to it. And so sitting down with pencil and paper, we were able to show that it's just a mathematical fact that if you take the longitudinal spectra and average in latitude, it's the very same thing as taking the 2D spectra and averaging in longitude. Okay, so you averaging over meridional wave number. Okay, so it's so you take the donut, you get squashed down to a pancake. Neither of which do we have out there, but I'm getting hungry talking about this. It's so the donut becomes a pancake, and that's what accounts for this flatlining behavior of the spectra. So in an unrelated discussion with Peter Sullivan, he pointed out to me, we in boundary layer meteorology, we know all about this stuff, and it's a problem. It's just aliasing. And I thought about that. I said, that's exactly what we have here. It's aliasing. It's so he brought out books off the shelf, Tennekes and Lumley, and so yeah, there it is. So for example, suppose you have a wave number vector over here, and the example that Tennekes and Lumley give is suppose you have like a one-dimensional array of sensors, and a wave comes by, and if that's all you know, then you'll estimate that the wavelength, the distance between the two crests here is lambda x, but you won't know that lambda is the actual scale. Now, if you have several waves at slightly different angles coming in, I got a blue wave and a red wave. I'm strictly nonpartisan in this seminar, and the one thing they have in common is they all overestimate lambda. You see, because they're all off the only ones that would get it right if you had wave crests being perpendicular to the sensor. Now, if you have an array, if you're lucky enough to have an array instead of just 1D, if you have multiple dimensions there, you can see by taking the one-dimensional Fourier transform at each latitude doesn't solve the problem because you still have aliasing at each point. The only way to find out what lambda is to do the two-dimensional Fourier transform, and from there you can determine what lambda is. Now, at this point in the conversation, when I explain it to folks, they say, "Well, what about this spectrum here? The aircraft whizzing back and forth across aren't they 1D spectra?" And yes, they are 1D spectra. And it turns out for 1D spectra, both of these methods, for power law spectrums, I should say, for power law, they both give the same answer. Because for power law, the peak is at the origin of the spectra. And so whether you integrate around the circle to produce a point or average over all the meridional wave numbers, you still get the same shape. So for power law, it's safe to do either one. But the thing is that the aircraft don't measure forecast error spectra. That's a creature of numerical models. And forecast error spectra are peaked at intermediate scales, and they grow. So just for grins, we did this hypothetical experiment. This is a specified. This is based on a specified donut ring in the theoretical model, and this is the growth of the error and scale. And then we do it by the 1D method, and that seems to produce these lines flying across the page here. And the same data analyzed through the very same data, through the 1D approach gives the impression that the growth in time is up-amplitude rather than upscale. And so we circled back to Falco and said, "Well, Falco, what happens if we take that spectra that you did in in spherical harmonics, which is sort of the equivalent of doing the 2D error spectra. And I take the same thing and do the longitudinal spectra and average from 60 north to 60 south. And you can see what happens here. It takes away all the information about the peak, and it makes those lines fly across the page. So you don't see in either the large scale or the small scale regimes here. You have the same sort of behavior. We tried to recognizing that most error spectra will not be homogeneous, horizontally homogeneous. We experimented a little bit in the paper with windowing. So here's that same error field that I show you that filled the whole plot, but now windowing down to a latitude band, and then showing again doing the 2D error spectra, and then reducing it to 1D by integrating around the circles. And the effect that it has in this case is it takes the full error spectrum at large error amplitude and just reduces it down a bit. So we went back to Falco's results and said, okay, let's try to apply this to Falco's results here. And we had a sort of a filter scale at about wave number 10, and it seems to capture the wave behavior of the spectrum for the larger wave numbers, smaller scales, but beyond the scale of the filter, it doesn't work, and obviously it doesn't work very well here either, because the filter is right about here. So but it's basically proposed methods that need to be worked on if you're going to do this sort of analysis. So this is my conclusion slide. I'm just going to bring back the basic slide that I introduced the results with. Is that the error energy spectrum of a 2D error field. And here's our 2D error field. Can be reduced to a 1D spectrum, either by doing the one-dimensional error energy spectrum in X and averaging over Y, or B, by doing the 2D error spectrum and summing around the annually for each kappa. And you, the analysts, you can do whatever you like, but only the second way is consistent with statistical predictability theory, in which the kappa represents the magnitude of the wave number vector in the 2D space. And I should say, for the three-dimensional turbulence guys in the audience, it would be a sphere instead of a circle on this sort of diagram. So as promised, I'm going to come back to this statement, the content of this statement. So now that you know what the difference is between 2D and 1D, the 2D error, and let's read the statement. The 2D errors are largest at small scales. Now we're referring to this one. They're larger at small scales and decrease with increasing wavelength. So if you go to larger scales, they now slope downward instead of coming across the page. Nevertheless, the error growth using both computational methods is primary up-amplitude, with relative errors growing at approximately the same rate at all scales. So what the authors are drawing your attention to is that the distance, say, between the red and the blue lines here at the large scale is pretty much the same as the distance at the small scale between the red and the blue line. So it's growing up amplitude in this definition, and it's pretty much the same as the red and the blue here. So the large scales are they're supporting the statement that that large scales grow just as rapidly as small scales across the range. So I thought, well, let's how do we look at this, Rotunno, Snyder, and Ute? Well, let's bring back predictability, the results from statistical predictability theory. This is from the paper by Mattei and Lesueur for the -5/3 spectrum, and here they're computing error spectrum for the -2, which is not that different than 1.67. So, what you note here is that, the error, it starts out at small scales and ends up at larger scales. It grows fast at the beginning and slows down as you go, slows down as you go. And to make this comparison a little bit easier on the eye, I did a little bit of a cutout here. They're about a little bit less than 3 decades across in X. And so I chose 3 decades across here of the theoretical spectra. And there are about 4 decades here in the Y direction, and I cut out about four decades here. So what I did through the magic of PowerPoint is I cropped it, resized it, and put these two things on the same playing field. Okay, so what you see here is that now the statistical predictability theory doesn't look so bad. You know, you see the errors growing upscale like this, and all of these lines here, yeah, they grow up amplitude, right? It's because you have each of these scales. You go to the large scales, and the distance between this line and this line is the same. But this is what comes out of statistical predictability theory. There's a fixed slope to the left there's a fixed slope of these lines to the left of the peaks, and that fixed slope implies up amplitude, right? But that's the wrong thing to focus on, I'd argue. The focus is that the scales at small scales, they grow fast, and they contaminate the next scale up. So I would argue that this figure doesn't disqualify statistical predictability theory, but on the other hand, it doesn't confirm it either, because of what we're all doing here is basically making these comparisons and citing them as circumstantial evidence that the theory applies or doesn't apply. And I think if someone wants to really advance this topic, the way to go is to actually develop a spectral error energy equation for these meteorological models. And then you could actually track how energy at these larger scales gain their energy over time. Does it come through nonlinear transfer or what? So anyway, with that I'll end and I'll take questions.
We have plenty of time for questions. Brian, do you want to start off? Hold on, let me give you the mic. Hopefully Dale will.
Yeah, I was warned myself long ago that we're being too cavalier when we use the word scale interchangeably with wave number. Because Fourier analysis isn't what it appears to be, and then there's this total wave number and all this stuff. So maybe all this talk of scale is not really even quite well defined, and we just need to be a little pricklier about our verbal description. But can you remind me again why E of k is equal to k times U of k? Where the 5/3 came from? Show me that again.
Sure. Let's. Yeah. Okay. So, right. So the first step is just 1 over the advective scale, and so what Doug did here is said, okay, well, is that velocity scale, and the only thing available in this is k and e, and you could form a velocity scale from those two things.
Because the square root of energy is velocity.
Yeah, k times
taking the square root gets you a factor of k.
No, k times e square root is velocity.
Oh.
Because the e is energy per unit wave number.
Per unit wave number. Yeah, this is the other thing I've always just thought.
Right. Yeah, if you look at the unit.
Bins of wave number.
Yeah, if you look at the units of this, there's an extra.
Right. And we use we use logarithms to smother that fact. But yeah.
Right. Yeah. So it's k of k.
Yeah.
Yeah.
Anyway, great to hear the methodology tidied up by someone like you.
Well, the thing is, it has it has practical implications because in my last exchange with Dale on email, I said, look, because the critical insight of Lorenz is that look, if you make resolution higher and higher, you're not going to win that game. Yes, it'll get marginally better, but it's not going to get tremendously better. So My last email with Dale was like, well, look, I'll bet you a case of beer that if Falco could redo his experiments with 10 times the resolution, the error is not going to be that different at 12 hours. And then he came back and said, we've already done that experiment. It's all right, great, fantastic. That means, that's the critical insight here, is that you can't proceed indefinitely with a forecast by making the initial condition better and better.
Maybe one more point I'd make is, 10 north to 10 south is a waveguide that maybe makes sense to treat longitudinally, whereas, 50 to 60 north, not so much, as part of a polar cap that really should be done more horizontally. So the Earth might have room for both. And these, global spectra that sort of
No, but I don't
cover
know, but-
both polar caps and the equatorial belt maybe are a little too coarse.
But if you do just the longitudinal spectrum and there's a two-dimensional variation in the error, then you're going to get this aliasing problem.
Yeah, I agree.
Yeah, two things I noticed. One, when you looked at that animation, there was, it looked like the tropics are more predictable than the mid-latitudes.
Falco's, you're right. Yeah, Falco's working on that.
And then the other point, I guess, was in the paper that Brian wrote, in the 1D cloud resolving model, the error growth is upscale and there's no issue with this. aliasing.
Okay, let's go to, which one you want to do first? Falco?
Yeah, let me just respond. Actually, Rich, can you move the slider all the way to the right, that it's at the end at the 20 days? Actually, if you go to the animation, you should be able to drag that.
Oh, I see what you mean, okay.
Yeah, so you don't have to wait a minute.
Right.
And
No, but I'm not getting it.
oh, there we go. Okay, I think that's good. So it's not normalized by the background, and what you're seeing essentially is just the squared difference between the U and V winds, and they're just much higher in the mid latitudes because you have jet streams and everything. So it's not normalized by the background energy in a sense. That's why you get this lighter color over the tropics. But there is actually more predictability in the tropics. In the other paper, I was hand-wavily arguing it's because of equatorial waves, and they're coming out of linear theory, and they're not disturbed by convective errors. But I think what you're seeing here is really just an artifact of that the winds are weaker in the tropics.
Oh, what was the second question? I forgot.
Could it also be that there aren't large-scale features that are developing in the tropics like they are at mid-latitudes? You're not developing a big synoptic scale wave. You only basically have the convection. And so it's always, the errors are always having, does that make any sense?
There's Kelvin waves.
They're okay.
large-scale synoptic scale features.
Okay. Way over on the right.
So much. Thank you. Very interesting. I guess my question is a little bit sort of following up on this. So a lot of this theory was developed in terms of turbulence and statistical models, etc. So my question goes along the lines, to which degree is the atmosphere really following this? What are the limitations? One of it is subseasonal prediction, right? Going this out, there shouldn't be skill in subseasonal, so could you comment on that? And the other one is even, so if you say adding fine scale or additional fine scale information has no effect on predictability because it's limited, so does it mean we don't need high resolution models? And so sort of, what about the fact that sometimes you need small scales to capture a particular process, and how does that relate to turbulence?
So which
Before you respond, we need high-resolution models to produce high-resolution features, right? Short-term features. So that's important as well, right?
I agree with you, but
Yeah.
yeah.
Okay. Go ahead.
All right, so I mean, it depends on, the target. Target forecast is important, like if the target here is 5 days, as in Ed Lorenz's example, then initializing at, 2 meters is not gonna help much. I mean, that's, if it's a turbulent flow, right, then you have to go over the statistical methods after that. And I think seasonal, then you're talking about the skill comes from boundary conditions, the ocean. I don't know much about it, actually. But it's very much focused on numerical weather prediction, this sort of thinking. Now, in order to answer that part of your question there is that my last slide, you need to have an equation for that actually tells you how the error in a particular scale is changing in time. What are the terms in the equation that, at least in the turbulence model, it's only one thing: nonlinear advection.
I have a question from your last slide. You mentioned that there isn't a spectral energy equation for meteorological data.
No, for meteorological models.
Sorry?
For meteorological models.
I'm surprised to hear that because, a lot of our models are written in spectral space. So why isn't there? And even if we write it down, how will it help?
Well, okay, so a spectral, you have a spectral equation for the actual forecast fields, but to do a spectral error, you have to have two equations, differing by a small amount, two solutions different, and you have to form the equation for the difference spectra. So we have spectral equations for the basic fields, but as far as I know, no one's formulated an equation for the difference between, in spectral space. So, a natural, add-on, some enterprising student want to look at Falco's results in, spherical harmonics, and you develop the equations then for, for the difference error in spherical harmonics. It would be a bear, but it would at least answer the question of how does one scale grow and how does it affect the next scale and the next scale.
On the last topic, Rich, okay, so I talked to these people who do surface gravity wave modeling. They don't use Navier-Stokes. They call it the wave action equation, and it's specifically written for the wave spectrum. On the right-hand side, there's specifically a term that's nonlinear interactions, and then they have something that makes the waves grow and something that makes them dissipate. So what happens then is that nonlinear wave action term actually makes the small ones grow into bigger and bigger waves. Let's say with fetch off the surface from the coastline. Is that the kind of thing you're thinking about, or is it still different?
It's still different. Yeah, it's really we have models that forecast U, U and V and W, right? So, but you want a model that will forecast the difference between one set of solutions and another set of solutions. So it'd be like if U1 dt equals stuff, U2 dt equals stuff. The only difference is they start out from a different initial condition. Okay, and then you take the Fourier transform of each one. Then you cross multiply by the, and you form the difference error in spectral. Right. So it's got all the nonlinear terms that you would have had, plus others. Right. And that's what's done. That's what's done in the statistical predictability theory. And it's fantastic. It's fantastically complicated. I can't claim to understand it all, but I know in principle what they do.
I'd like to invite everybody to continue this discussion outside at this point.
No pancakes, no donuts.
Maybe you can solve the problem over donuts and whatever, or just socialize. And otherwise, let's thank Rich again for a great seminar.
Thank you.